The Euler angles are three angles introduced by Leonhard Euler to describe the orientation of a rigid body. To describe such an orientation in three-dimensional Euclidean space, three parameters are required. They can be given in several ways, Euler angles being one of them. See charts on SO3 for others. Euler angles are also used to represent the orientation of a frame of reference relative to another. They are typically denoted as I plus or minus, I squared, I cubed, or. Euler angles also represent a sequence of three elemental rotations, that is, rotations about the axis of a coordinate system. For instance, a first rotation about z by an angle I plus or minus, a second rotation about x by an angle I squared, and a last rotation again about z, by an angle I cubed. These rotations start from a known standard orientation. In physics, this standard initial orientation is typically represented by a motionless coordinate system. In linear algebra, by a standard basis. Any orientation can be achieved by composing three elemental rotations. The elemental rotations can either occur about the axis of the fixed coordinate system or about the axis of a rotating coordinate system, which is initially aligned with the fixed one, and modifies its orientation after each elemental rotation. The rotating coordinate system may be imagined to be rigidly attached to a rigid body. In this case, it is sometimes called a local coordinate system. Without considering the possibility of using two different conventions for the definition of the rotation axis, there exist 12 possible sequences of rotation axes, divided in two groups: Euler angles, Tait-Bryan angles. Tait-Bryan angles are also called Cardan angles, Nautical angles, heading, elevation, and bank, or yaw, pitch, and roll. Sometimes, both kinds of sequences are called Euler angles. In that case, the sequences of the first group are called proper or classic Euler angles. Proper Euler angles. Classic definition: Euler angles are a means of representing the spatial orientation of any reference frame as a composition of three elemental rotations starting from a known standard orientation, represented by another frame. The reference orientation can be imagined to be an initial orientation from which the frame virtually rotates to reach its actual orientation. In the following, the axes of the original frame are denoted as x, y, z, and the axes of the rotated frame are denoted as x, y, z. In geometry and physics, the rotated coordinate system is often imagined to be rigidly attached to a rigid body. In this case, it is called a local coordinate system, and it is meant to represent both the position and the orientation of the body. The geometrical definition of the Euler angles is based on the axes of the above-mentioned reference frames and an additional axis called the line of nodes. The line of nodes is defined as the intersection of the xy and the xy coordinate planes. In other words, it is a line passing through the origin of both frames, and perpendicular to the zz plane, on which both z and z lie. The three Euler angles are defined as follows: I plus or minus is the angle between the x-axis and the n-axis. I squared is the angle between the z-axis and the z-axis. I cubed is the angle between the n-axis and the x-axis. This definition implies that I plus or minus represents a rotation around the z-axis, I squared represents a rotation around the n-axis, I cubed represents a rotation around the z-axis. If I squared is 0, there is no rotation about n. As a consequence, z coincides with z, I plus or minus and I cubed represent rotations about the same axis, and the final orientation can be obtained with a single rotation about z, by an angle equal to I plus or minus plus I cubed. Alternative definition: the rotated frame xyz may be imagined to be initially aligned with x's, before undergoing the three elemental rotations represented by Euler angles. Its successive orientations may be denoted as follows: xyz, or xoyozo, ZA Euro unregistered trademark YA Euro unregistered trademark ZA Euro unregistered trademark, or x1y1z1, ZA Euro cubed YA Euro cubed ZA Euro cubed, or x2y2z2, xyz, or x3y3z3. For the above listed sequence of rotations, The line of nodes n can be simply defined as the orientation of x after the first elemental rotation. Hence, n can be simply denoted as our Euro unregistered trademark. Moreover, since the third elemental rotation occurs about z, it does not change the orientation of z, hence z coincides with z Euro cubed. This allows us to simplify the definition of the Euler angles as follows: I plus or minus represents a rotation around the z-axis, I squared represents a rotation around the z Euro unregistered trademark axis, I cubed represents a rotation around the z Euro cubed axis. Conventions: different authors may use different sets of rotation axes to define Euler angles, or different names for the same angles. Therefore any discussion employing Euler angles should always be preceded by their definition. Unless otherwise stated, this article will use the convention described above. The three elemental rotations may occur either about the axis x of the original coordinate system, which is assumed to remain motionless, or about the axis of the rotating coordinate system x, y, z, which changes its orientation after each elemental rotation. The definition above uses intrinsic rotations. There are 6 possibilities of choosing the rotation axis for proper Euler angles. In all of them, the first and third rotation axis are the same. The 6 possible sequences are z Euro unregistered trademark z Euro cubed or zxz, x Euro unregistered trademark z Euro cubed or xyx, y Euro unregistered trademark Euro cubed or yzy, z Euro unregistered trademark z Euro cubed or zyz, x Euro unregistered trademark z Euro cubed or xzx, y Euro unregistered trademark Euro cubed or yxy. Euler angles between two reference frames are defined only if both frames have the same handedness. Sines and ranges: angles are commonly defined according to the right-hand rule. Namely, they have positive values when they represent a rotation that appears counterclockwise when observed from a point lying on the positive part of the rotation axis, and negative values when the rotation appears clockwise. The opposite convention is less frequently adopted. About the ranges: for I plus or minus and I cubed, the range is defined modulo 2 Euro radians. A valid range could be I Euro, I Euro. For I squared, the range covers Euro radians. For example could be 0, I Euro or I 2 euros. The angles I plus or minus, I squared and I cubed are uniquely determined except for the singular case that the xy and the xy planes are identical, the z-axis and the z-axis having the same or opposite directions. Indeed, if the z-axis and the z-axis are the same, I squared equals A0 and only is uniquely defined, and, similarly, if the z-axis and the z-axis are opposite, I squared equals AI Euro and only is uniquely defined. These ambiguities are known as Gimbal lock-in applications. Geometric derivation. The fastest way to get the Euler angles of a given frame is to write the 3 given vectors as columns of a matrix and compare it with the expression of the theoretical matrix. Hence the 3 Euler angles can be calculated. Nevertheless, the same result can be reached avoiding matrix algebra, which is more geometrical. Assuming a frame with unit vectors as in the main diagram, it can be seen that and since we have, as is the double projection of a unitary vector. There is a similar construction for projecting it first over the plane defined by the axis z and the line of nodes. As the angle between the planes is and, this leads to. And finally, using the inverse cosine function. It is interesting to note that the inverse cosine function yields 2 possible values for the argument. In this geometrical description only one of the solutions is valid. When Euler angles are defined as a sequence of rotations, all the solutions can be valid, but there will be only one inside the angle ranges. This is because the sequence of rotations to reach the target frame is not unique if the ranges are not previously defined. For computational purposes, it may be useful to represent the angles using a tan 2, y, x. Tait-Bryan angles. The second type of formalism is called Tait-Bryan angles, after Peter Guthrie Tait and George H. Bryan. The definitions and notations used for Tait-Bryan angles are similar to those described above for proper Euler angles. The only difference is that Tait-Bryan angles represent rotations about three distinct axes, while proper Euler angles use the same axis for both the first and third elemental rotations. This implies a different definition for the line of nodes. In the first case it was defined as the intersection between two homologous Cartesian planes. In the second one, it is defined as the intersection of two non-homologous planes. Conventions: the three elemental rotations may occur either about the axis of the original coordinate system, which remains motionless, or about the axis of the rotating coordinate system, which changes its orientation after each elemental rotation. There are 6 possibilities of choosing the rotation axis for Tait-Bryan angles. The 6 possible sequences are x(Euro unregistered trademark (Euro cubed or XYZ), y(Euro unregistered trademark (Euro cubed or YZX), z(Euro unregistered trademark (Euro cubed or ZXY), x(Euro unregistered trademark (Euro cubed or XZY), z(Euro unregistered trademark (Euro cubed or ZYX), y(Euro unregistered trademark (Euro cubed or YXZ). Alternative names. Tait-Bryan angles are also known as nautical angles, because they can be used to describe the orientation of a ship or aircraft, or Cardan angles, after the Italian mathematician and physicist Girolamo Cardano, who first described in detail the Cardan suspension and the Cardan joint. They are also called heading, elevation and bank, or yaw, pitch and roll. Notice that the second set of terms is also used for the 3 aircraft principal axes. Relationship with physical motions. Intrinsic rotations. Intrinsic rotations are elemental rotations that occur about the axis of the rotating coordinate system XYZ, which changes its orientation after each elemental rotation. The XYZ system rotates, while axis is fixed. Starting with XYZ overlapping axes, a composition of 3 intrinsic rotations can be used to reach any target orientation for XYZ. The Euler or Tait-Bryan angles are the amplitudes of these elemental rotations. For instance, the target orientation can be reached as follows: the XYZ system rotates by I plus or minus about the z-axis. The x-axis now lies on the line of nodes. The XYZ system rotates about the now rotated x-axis by I squared. The z-axis is now in its final orientation, and the x-axis remains on the line of nodes. The XYZ system rotates a third time about the new z-axis by I cubed. The above-mentioned notation allows us to summarize this as follows: the 3 elemental rotations of the XYZ system occur about z, (Euro unregistered trademark and (Euro cubed). Indeed, this sequence is often denoted z(Euro unregistered trademark (Euro cubed). Sets of rotation axes associated with both proper Euler angles and Tait-Bryan angles are commonly named using this notation. Sometimes, the same sequence is simply called ZXZ, ZXZ, or 3-1-3, but this notation may be ambiguous as it may be identical to that used for extrinsic rotations. In this case, it becomes necessary to separately specify whether the rotations are intrinsic or extrinsic. Rotation matrices can be used to represent a sequence of intrinsic rotations. For instance, represents a composition of intrinsic rotations about axis x(Euro unregistered trademark (Euro cubed), if used to pre-multiply column vectors, while represents exactly the same composition when used to post-multiply row vectors. See ambiguities in the definition of rotation matrices for more details. Extrinsic rotations. Extrinsic rotations are elemental rotations that occur about the axis of the fixed coordinate system axis. The XYZ system rotates, while axis is fixed. Starting with XYZ overlapping axes, a composition of 3 extrinsic rotations can be used to reach any target orientation for XYZ. The Euler or Tait-Bryan angles are the amplitudes of these elemental rotations. For instance, the target orientation can be reached as follows: the XYZ system rotates about the z-axis by I plus or minus. The x-axis is now at angle I plus or minus with respect to the x-axis. The xyz system rotates again about the x-axis by I squared. The z-axis is now at angle I squared with respect to the z-axis. The xyz system rotates a third time about the z-axis by I cubed. In sum, the three elemental rotations occur about z, x and z. Indeed, this sequence is often denoted zxz. Sets of rotation axes associated with both proper Euler angles and Tait-Bryan angles are commonly named using this notation. Rotation matrices can be used to represent a sequence of extrinsic rotations. For instance, represents a composition of extrinsic rotations about axes x, y, z, if used to pre-multiply column vectors, while represents exactly the same composition when used to post-multiply row vectors. See ambiguities in the definition of rotation matrices for more details. Conversion between intrinsic and extrinsic rotations. Any extrinsic rotation is equivalent to an intrinsic rotation by the same angles but with inverted order of elemental rotations, and vice versa. For instance, the intrinsic rotations x are euro unregistered trademarks are euro cubed by angles I plus or minus, I squared, I cubed are equivalent to the extrinsic rotation zyx by angles I cubed, I squared, I plus or minus. Both are represented by a matrix. If R is used to pre-multiply column vectors, and by a matrix. If R is used to post-multiply row vectors. See ambiguities in the definition of rotation matrices for more details. Euler basic motions and Gimbal analogy. Euler basic motions are defined as the movements obtained by changing one of the Euler angles while leaving the other two constant. Euler rotations are never expressed in terms of the external frame, or in terms of the co-moving rotated body frame, but in a mixture. They constitute a mixed axis of rotation system, where the first angle moves the line of nodes around the external axis z, the second rotates around the line of nodes and the third one is in intrinsic rotation around an axis fixed in the body that moves. These rotations are called precession, nutation, and intrinsic rotation. As an example, consider a top. The top spins around its own axis of symmetry. This corresponds to its intrinsic rotation. It also rotates around its pivotal axis, with its center of mass orbiting the pivotal axis. This rotation is a precession. Finally, the top can wobble up and down. The inclination angle is the nutation angle. While all three are rotations when applied over individual frames, only precession is valid as a rotation operator, and only precession can be expressed in general as a matrix in the basis of the space. Gimbal analogy. If we suppose a set of frames, able to move each with respect to the former according to just one angle, like a gimbal, there will exist an external fixed frame, one final frame and two frames in the middle, which are called intermediate frames. The two in the middle work as two gimbal rings that allow the last frame to reach any orientation in space. In these conditions, each Euler rotation works on one of the rings, independently from the rest. Intermediate frames. The gimbal rings indicate some intermediate frames. They can be defined statically too. Taking some vectors I, j and k over the axes x, y and z, and vectors I, j, k over x, y and z, and a vector n over the line of nodes, some intermediate frames can be defined using the vector cross product, as following: origin, I, j, k, first, n, k, n, k, second, n, k, n, k, final, I, j, k. These intermediate frames are equivalent to those of the gimbal. They are such that they differ from the previous one in just a single elemental rotation. This proves that any target frame can be reached from the reference frame just composing three rotations. The values of these three rotations are exactly the Euler angles of the target frame. Relationship to other representations. Euler angles are one way to represent orientations. There are others, and it is possible to change to and from other conventions. Rotation matrix. Any orientation can be achieved by composing three elemental rotations, starting from a known standard orientation. Equivalently, any rotation matrix R can be decomposed as a product of three elemental rotation matrices. For instance, is a rotation matrix that may be used to represent a composition of intrinsic rotations about axis x Euro unregistered trademarks Euro cubed. However, both the definition of the elemental rotation matrices x, y, z, and their multiplication order depend on the choices taken by the user about the definition of both rotation matrices and Euler angles. Unfortunately, different sets of conventions are adopted by users in different contexts. The following table was built according to this set of conventions. Each matrix is meant to operate by pre-multiplying column vectors. Each matrix is meant to represent an active rotation. Each matrix is meant to represent the composition of intrinsic rotations. Right-handed reference frames are adopted, and the right-hand rule is used to determine the sign of the angles I plus or minus, I squared, I cubed. For the sake of simplicity, the following table uses the following nomenclature: 1, 2, 3 represent the angles I plus or minus, I squared, I cubed. X, Y, Z are the matrices representing the elemental rotations about the axis X, Y, Z of the fixed frame. S and C represent sine and cosine. Each matrix is denoted by the formula used to calculate it. If we name it. To change the formulas for the opposite direction of rotation, change the signs of the sine functions. To change the formulas for passive rotations, transpose the matrices. Quaternions, unit quaternions, also known as Euler or Euro-Rodrigues parameters, provide another mechanism for representing 3D rotations. This is equivalent to the special unitary group description. Expressing rotations in 3D as unit quaternions instead of matrices has some advantages. Concatenating rotations is computationally faster and numerically more stable. Extracting the angle and axis of rotation is simpler. Interpolation is more straightforward. See for example slope. Geometric algebra. Other representation comes from the geometric algebra, GA. GA is a higher-level abstraction, in which the quaternions are an even subalgebra. The principal tool in GA is the rotor-wear angle of rotation, rotation axis in pseudosquare, properties. The Euler angles form a chart on all of SO3, the special orthogonal group of rotations in 3D space. The chart is smooth except for a polar coordinate-style singularity along I squared equals 0. See charts on SO3, for a more complete treatment. The space of rotations is called in general the hypersphere of rotations, though this is a misnomer. The group spin, 3, is isometric to the hypersphere S3, but the rotation space SO3 is instead isometric to the real projective space RP3, which is a two-fold quotient space of the hypersphere. This 2-to-1 ambiguity is the mathematical origin of spin in physics. A similar three-angle decomposition applies to SU2, the special unitary group of rotations in complex 2D space, with the difference that I squared ranges from 0 to 2I Euro. These are also called Euler angles. The Haar measure for Euler angles has the simple form sin, I squared d plus or minus d squared d cubed, usually normalized by a factor of 1/8I Euro a squared. For example, to generate uniformly randomized orientations, let I plus or minus and I cubed be uniform from 0 to 2I Euro, let z be uniform from a 1 to 1, and let I squared equals arc cos z. Higher dimensions, it is possible to define parameters analogous to the Euler angles in dimensions higher than 3. The number of degrees of freedom of a rotation matrix is always less than the dimension of the matrix squared. That is, the elements of a rotation matrix are not all completely independent. For example, the rotation matrix in dimension 2 has only 1 degree of freedom, since all 4 of its elements depend on a single angle of rotation. A rotation matrix in dimension 3 has 3 degrees of freedom, corresponding to each independent rotation, for example by its 3 Euler angles or a magnitude 1 quaternion. In SO4, the rotation matrix is defined by 2 quaternions, and is therefore 6 parametric. The 4A, 4 rotation matrices have therefore 6 out of 16 independent components. Any set of 6 parameters that define the rotation matrix could be considered an extension of Euler angles to dimension 4. In general, the number of Euler angles in dimension d is quadratic in d. Since any one rotation consists of choosing 2 dimensions to rotate between, the total number of rotations available in dimension is, which for yields. Applications: vehicles and moving frames. Their main advantage over other orientation descriptions is that they are directly measurable from a gimbal mounted in a vehicle. As gyroscopes keep their rotation axis constant, angles measured in a gyro frame are equivalent to angles measured in the lab frame. Therefore gyros are used to know the actual orientation of moving spacecraft, and Euler angles are directly measurable. Intrinsic rotation angle cannot be read from a single gimbal, so there has to be more than one gimbal in a spacecraft. Normally there are at least 3 for redundancy. There is also a relation to the well-known gimbal lock problem of mechanical engineering A. The most popular application is to describe aircraft attitudes, normally using a Tait-Bryan convention so that 0 degrees elevation represents the horizontal attitude. Tait-Bryan angles represent the orientation of the aircraft respect a reference axis system with 3 angles which in the context of an aircraft are normally called heading, elevation and bank. When dealing with vehicles, different axis conventions are possible. When studying rigid bodies in general, one calls the x system space coordinates, and the XYZ system body coordinates. The space coordinates are treated as unmoving, while the body coordinates are considered embedded in the moving body. Calculations involving acceleration, angular velocity, angular momentum, and kinetic energy are often easiest in body coordinates, because then the moment of inertia tensor does not change in time. If one also diagonalizes the rigid body's moment of inertia tensor, then one has a set of coordinates in which the moment of inertia tensor has only 3 components. The angular velocity of a rigid body takes a simple form using Euler angles in the moving frame. Also the Euler's rigid body equations are simpler because the inertia tensor is constant in that frame. Others, Euler angles, normally in the Tait-Bryan convention, are also used in robotics for speaking about the degrees of freedom of a wrist. They are also used in electronic stability control in a similar way. Gun-fire control systems require corrections to gun order angles to compensate for deck tilt. In traditional systems, a stabilizing gyroscope with a vertical spin axis corrects for deck tilt, and stabilizes the optical sights and radar antenna. However, gun barrels point in a direction different from the line of sight to the target, to anticipate target movement and fall of the projectile due to gravity, among other factors. Gun mounts roll and pitch with the deck plane, but also require stabilization. Gun orders include angles computed from the vertical gyro data, and those computations involve Euler angles. Euler angles are also used extensively in the quantum mechanics of angular momentum. In quantum mechanics, explicit descriptions of the representations of SO(3) are very important for calculations, and almost all the work has been done using Euler angles. In the early history of quantum mechanics, when physicists and chemists had a sharply negative reaction towards abstract group theoretic methods, reliance on Euler angles was also essential for basic theoretical work. In materials science, crystallographic texture can be described using Euler angles. In texture analysis, the Euler angles provide the necessary mathematical depiction of the orientation of individual crystallites within a polycrystalline material, allowing for the quantitative description of the macroscopic material. The most common definition of the angles is due to Bunge and corresponds to the ZXZ convention. It is important to note, however, that the application generally involves axis transformations of tensor quantities, that is passive rotations. Thus the matrix that corresponds to the Bunge-Euler angles is the transpose of that shown in the table above. Many mobile computing devices contain accelerometers which can determine these devices' Euler angles with respect to the Earth's gravitational attraction. These are used in applications such as games, bubble-level simulations, and kaleidoscopes. See also, 3D projection, axis angle representation, conversion between Quaternions and Euler angles, Euler's rotation theorem, Quaternions and spatial rotation, rotation formalisms in 3 dimensions, spherical coordinate system, references. Bibliography, Weidenhahn, L.C. Luke, J.D., Angular Momentum in Quantum Physics, Reading, Massachusetts, Edison Euro Wesley, ISBN A978-0-201-13507-7 Goldstein, Herbert, Classical Mechanics, Reading, Massachusetts, Edison Euro Wesley, ISBN A978-0-201-02918-5 Gray, Andrew, A Treatise on Gyrostatics and Rotational Motion, London, Macmillan, ISBN A978-1-4212-5592-7 Rose, M.E., Elementary Theory of Angular Momentum, New York New. John Wiley & Sons, ISBN A978-0-486-68480-2 Simon, Keith, Mechanics, Reading, Massachusetts, Addison Wesley, ISBN A978-0-201-07392-8 Landau, L.D. Lifshitz, E.M., Mechanics, Oxford, Butterworth Heinemann, ISBN A978-0-7506-2896-9 External links, Westerheim, Eric W., Euler angles, MathWorld. JavaApplet for the simulation of Euler angles available at http://www.paralemic.org Euler angles HTML. Euler angles, an iOS app for visualizing in 3D the 3 rotations associated with Euler angles. http SourceForge Nita Iliba A collection of routines for rotation/orientation manipulation, including special tools for crystal orientations. Online tool to compose rotation matrices available at http://www.vectoralgebra.info/. EulerMatrix.html